Hey, it's Miss Matt here with your Unit 5 review for the end of unit assessment. So I just went ahead on number 1 to get started as I kind of like wrote in what the transformations are. So we have P of x, which is the solid curve, and then the data set is G of x, and we want to know how to get from P of x to G of x. So then we want to write an equation for G in terms of P of x. So to get this set of data points here, we want to take the function and shift it to the right 3 and up 2. And the way that we do that using function notation is we say G of x is equal to P of, shifting to the right 3 gives us x minus 3, and then up 2 would be a plus 2 right there. Okay, so same idea for the next one. We have to go right 2 and up 1. I drew that little pathway in, right 2 and up 1 to get those to match up. And so G of x is equal to P of right 2 is x minus 2, and up 1 is plus 1 on the outside. So if we're moving left and right, that's a change to input. Up and down, that's a change to output. So input changes go in the parentheses, output changes go outside the parentheses. All right. For the second two here, we actually decided not to do this one because there's a little tiny problem with it. So we just kind of said, don't do it. It's fine. There's plenty of practice in what you need in the other three that it's fine that we just don't do that last one. But here, for this, it's like a parabola. I can tell it's been reflected over the x. So that's changing the y values. That's an output change when you reflect over the x, because it's the y's that were positive here are going to just flip over and be the opposite. And then the vertex, I didn't draw the path in for this one, but I will. The vertex is going to go right from 0, 0 to the right 2, and then up 5 to get to that point right there. So that means this will be G of x equal to, all right, so when we reflect over the x-axis, our negative goes in front of P of x. And then we have to go to the right 2. So again, it's like the opposite to what you would think. So instead of plus, minus, and then up 5, that's an output change, so plus 5 out there. All right, in the next section, it says the functions g and r are related by the equations below. Describe a sequence of transformations that will take the graph of f to the graph of g. So we're just looking at here, like what are all of the parts that don't just say f of x, what are they doing? So I know this piece is reflecting over the over the x-axis, and then this is to the right too. So reflect over the x-axis, and then shift right 2. Then when we have the negative inside and it's a change to the input, that's reflecting over the y-axis, because on the left side of the y-axis, that's where the x values are negative. On the right side of the y-axis, that's where x values are positive. So when we change the sign of x, it makes it reflect over the y-axis. So reflect over the y-axis and shift up 1. Alrighty. Next, we've got a couple more things going on here because it's not just negative, it's negative 2. And so that's a vertical stretch since the 2 is greater than 1. So we're going to reflect over the x-axis. vertical stretch by a factor of 2, and then shift to the left 1. And then finally, on the last one here, this time our scale is on the X. We're scaling the X, and so that's a horizontal scale. But remember that when you scale the inputs, it's like the opposite thing happens. So a scale of 1/2 actually is a stretch of 2. This would need to be a 2 to have a compression of 1/2. So it's actually being stretched by 2, the reciprocal of 1/2. So this is a horizontal stretch by 2, and then shifting to the right, or sorry, to the left 4, and down 2. So horizontal stretch by 2, and then shift left 4, down 2. Okay. Page 1 is done. Page 2. I kind of got a little bit started here on page 2, just kind of creating the start of the table. So I noticed a couple of things that made me choose these values for X. So basically we have to figure out when we add the outputs of those two functions together, what's our new point? And I noticed that there just weren't a lot of like whole number points to work with here. So I figured like when X is, I kind of just looked at the line to begin with. When X is -9 here, this is on a whole number, and then every other point after that is on a whole number. I always want to include 0, so I did put 0 on the table, but otherwise I just counted by 2s, so I had whole number points to work with. So the first set of points, when X is -9, and we're adding the functions together, g of X is right here at -7, and f of X is here at about 2.5. And these, I mean, it's following an asymptote. So these are all about 2.5. Then this is 3, and it just gets bigger and bigger from there. So I'm going to use a lot of 2.5s. And then when X is, okay, like we said, -9, this is at -7, and then this is at -6, this is at -5, -4, -3, like -2.5, and so on. Okay, so I'm going to write some of those down in the table and see what that starts to look like. So again, we're adding -7 to about 2.5. -7 plus 2.5 is, let's see here, -4.5. And then this is -6 plus 2.5, which is -3.5. Kind of ran out of room there. This is when X is -5, -5 plus 2.5, which is -2.5. And then here at -3, this is at +3. So -3 plus 3 is 0. Oh, wait. Oh, I went 1 point too far. Sorry. Here's -3. This one's at -4. That one's at 2.5 still. -4 plus 2.5 is -1.5. Then we have where this is at -3, this is at +3. That happens when X is -1. So -3 plus 3, that's 0. And then here at 0, I have 1, 2, about 3.5 and negative 2.5. So negative 2.5 plus 3.5 is 1. And then I just went up to 1, which is here. This is at negative 2. And this is at, what is that? Looks like about 4.5. And maybe I'll just do one more point because I can kind of get something here. So when x is 2, this is at like negative 1.5. This is at about 6.5. So negative 1.5 plus 6.5 is 5. Okay, so I have a lot of points we can put on the graph. So for each point, this is the x, this is the new y. This is the x, this is the new y, and so on. Okay, so I'm going to put them on here. Negative 9, negative 4.5 is right here. Negative 7, negative 3.5 here. Negative 5, negative 2.5. And negative 3, negative 1.5. It's like all lining up, which makes sense because we're like adding an asymptote, almost the same number each time. Let's see, I was at negative 3, so negative 1, 0. Okay, negative 1, 0. So it must have to curve somehow, since that's a little further. 1 or 0, 1, 0, 1, 1, 2.5, and 2, 5. 1, 2, up to 5. Okay, so this is what the new function h of x, which is the combination of f of x plus g of x, looks like. Something like that. So for which values of x is h of x greater than 0? So h of x is greater than 0 above the x-axis. So we have our x-axis here. Okay, above this axis is where h of x is greater than 0, which means that below this axis is where h of x is less than 0. This is where the outputs are positive up here. This is where the outputs are negative down here. And so when does that happen? Well, it happens after the function crosses the x-axis, which it does so right here at negative 1. So any value greater than negative 1 for x is where these become positive. They're up on the positive side. So then where is it less than 0? On the other side of negative 1. The x-intercept is negative 1, 0. Okay, so here's the x-intercept. Any points this way are positive, any points this way are negative. And the y-intercept is this one right here. That's when x is 0, y is 1. All right. Moving on from there. So basically for this next problem, we're just looking at scaling the inputs, scaling the outputs, and what that means in context. So the k of t is the distance that Julian is as he's walking as a function of time. And then all of these are in relation to how far and how fast Julian walks. So since k of t is the output, it's the distance in miles, and t is the input, it's the time. When I have a 3 outside here, that means that the distance is being multiplied by 3. So this means somebody going 3 times as far as Julian went, but only half the speed or half as fast. So out of these options, which one says 3 times further, half the pace? This is B. So this would be A of x, which is 3 k of 1/2 t. Okay, so I got that one. The next one, this is like half the distance, but 3 times as fast. So he's walking much faster, but half the distance. Half the distance, 3 times as fast. Looks like this one. Half as far, 3 times faster. So that's B of x. Half the distance means the 1/2 goes in front. 3 times as fast means the 3 goes there inside. It's scaling the t. All right, and then the last one, walking 3 times further than Julian and twice as fast. That makes sense that it would be here for C, 3 times further, twice as fast. So this is C of x. 3 times further, 3 goes in front of the k, and then twice as fast, k of 2t. All right, and then we have one more question, kind of goes with the same prompt. Write a new function, d of x, for a student who walks 5 times further than Julian and 1.5 times faster. So the 5 is going to scale the output. It goes first. And the 1.5 scales the input. It goes in the parentheses, 1.5t. And there we go. Okay, this next problem is talking about meat. 2 pieces of meat are taken out of the freezer to thaw. The function m models the temperature of the meat, m of t, in Fahrenheit, t hours after it was taken out. The function k models the temperature of meat, k of t, in Fahrenheit, t hours after it was taken out. Here are the graphs of m and k. All right. So I noticed that they both have this 0, 13 and then 5, 13. Okay, and then the temperature is increasing because the meat is thawing. So first of all, explain what m of 3 equals 42.6 means in this context. It means that for this first graph, it means that after 3 hours, the temperature of the meat is 42.6 degrees Fahrenheit. How are the graphs the same and how are they different? Well, they're the same because they are representing the meat thawing at the same rate. But they're different because K of T was taken out of the freezer 5 hours after M of T. So that means they have, it's been shifted. So it's been shifted to the right 5 because it's 5 hours later. So if we write an expression in terms of M of T, so K of T equals M of, so if we go back to thinking about, if I know that K of 5, this point right here, is equal to M of 0, right? They're both equal to 13. So when the input is 5 for K, it's the same as when the input is 0 for M. That relationship is 5 minus 5. So this is going to be T minus 5. So the temperature over here, the time over here, relates to a time that was 5 hours earlier over here, because this one was taken out 5 hours later. And then finally, Julie takes a package of meat out of the freezer, but puts it in the refrigerator, so it thaws out half as fast as M of T. Sketch a graph of this on the same graph with M of T. If the function models Julie's package of meat, write a rule for J of T in terms of M of T using function notation. So if it's going to just be half, but starting at the same time. Okay. So that means that for Julie, if it's going half as fast, it's going to take twice as long, right? So it's going to start at the same point, but here, where this is only at 1, it's going to take Julie's 2, right? Because it's going to take twice as long. Here, when this takes 2 hours, this point will take Julie's meat package 4 hours. It's twice as long. The next one, where this is, let's see, 3 hours is here. 3 times 2 is 6. So here's 4, 5, 6, like that. Here's the data for M of T at 4 hours. 4 times 2 is 8. So 4, 5, 6, 7, 8. Okay, so that's probably good enough. It's going to look something like this. Not going to thaw as quickly. And then we have to write a rule. So if this is, if I just kind of make, let's see, this point right here, I'm going to call it J of 8. It's at the same height as M of 4. They have the same output, J of 8 and M of 4. So if I know that J of 8 is equal to M of 4, this is half of 8, right? So in general, J of T is equal to M of 1/2 T. Okay, and that's the first 3 pages. The next 2 will come to you in a separate video.